Okay, everybody, happy Friday. Welcome to you. I realize this is not the best time of morning to be taking a class. I have a son who's in his second year here, and he says he will never, ever take a class at 8 a.m. So I'm sorry for whatever circumstances conspired to make you here right now. If it's any consolation, I was up earlier than you. Every other Friday I have an assignment to play the organ in the chapel at the temple, which is kind of fun. So, yeah, you want to come see my gig Friday mornings? It's not that good, and there's not that much to play, but it's pretty fun. Okay, so we're finishing our introductory section and moving on to Chapter 2. We've done the last part of Chapter 2 sort of already, as we've talked about HOMO and LUMO and nucleophiles and electrophiles. As I've said, nucleophiles are molecules that have a high energy pair of electrons that is ready to be lowered in energy by interacting with some other empty orbital. An electrophile is a molecule that has a low energy empty orbital that is ready and available to accept electrons from a nucleophile. So the reason we've been spending so much time on HOMO and LUMO is that, as shown here, the first and great commandment of OCHEM, if you want to summarize OCHEM while standing on one foot, the first and great commandment of OCHEM is nucleophile attacketh electrophile, and the second is like unto it, HOMO attacketh LUMO. On these two hang all the rules and the reactions. Okay, so most reactions, and I'm still standing on one foot. That actually worked out better than I thought it was going to. Most of the reactions we'll talk about this semester and in 352 all involve this. And if you understand this, you can draw a pretty reasonable first mechanistic step for a reaction, even if you don't recognize the reaction or understand what's going on. So, for example, addition reactions. We've seen one of these before. We talked about BH3 last time. We're going to learn in the rest of Chapter 2, by the way, how to recognize good nucleophiles and good electrophiles. For now, you can just accept what I'm telling you as to who's the good nucleophile and who's the good electrophile. This is the LUMO of BH3. It's this empty p orbital, and you should get good at recognizing that. And then whatever our nucleophile is, let's suppose it's water. Water has, the HOMO is non-bonding lone pair electrons on oxygen. So the first step of this addition reaction should be HOMO attacks LUMO. So you draw an arrow from the electron pair to the LUMO, and then in terms of what happens next, it depends on the kind of empty orbital you're working with. In this case, the empty orbital is a p orbital. It's not an anti-bonding orbital. So actually, all that we've done in this reaction is we've made a bond, and that's it. All right, and I showed you that last time. We don't need to belabor that point. But there's other kinds of addition reactions in OCHEM, some of which you'll see later this semester, others of which you won't see until 352. For example, let's suppose I have this alkene, and suppose I want to react it with HCl. I will tell you that HCl is the electrophile. It's a dead giveaway because it has acid in its name, and electrophiles are Lewis acids. And the alkene is your nucleophile. What is the HOMO of this alkene? The pi bond, right? Which I can envision if I want to, if I'm looking at this molecule sort of from the side as two p orbitals lined up together with the same wave function sign, or alternatively, if I wanted to, I could draw a large lobe here and another large lobe there and color them in. That's fine too. Unfortunately, you can put this in the end of semester reviews. I am all too willing to waste precious class time coloring. But anyway, okay, so what is the LUMO of HCl? Sigma star, that's the only thing it actually can be, right? And the sigma star, we're going to say, has a node in between hydrogen and chlorine, and it's going to look something like this. And we need just opposite wave function signs on each side of the node. All right? Now, HOMO attacks LUMO, so you should draw an electron. You should draw an arrow starting with the pi electrons to the LUMO. But in this case, the LUMO's in more than one place. It's on both hydrogen and Cl. How do you know which one it should be? For this, you can basically turn to your electronegativity tools. There's more to it than this, but this is a reasonable way to reason through it. Chlorine is more electronegative than hydrogen. Therefore, chlorine should have a partial negative on it. Hydrogen should have a partial positive on it. Everybody okay with that? Yes? Yes? Okay. So we're going to draw our arrow from our nucleophile towards the electron deficient part of our molecule, and we're going to attack the LUMO there. Now, this reaction is different from the one we just did because we're dumping electrons into an antibonding orbital, and that tells you that something happens next. Okay, what should happen if I dump electrons in an antibonding orbital? I make a new bond on one side, but I got to break the other one, right? So we're going to show that as these electrons move to chloro, and then we can predict that one of the products here is going to be Cl minus. Now, here's an interesting question. The pi electrons attack the hydrogen. The pi electrons were shared between two carbons, 1 and 2 we'll call them. Which carbon gets the hydrogen? Could it be in resonance? Actually, so geek out for a moment. Please do not write this down. Please do not worry about it. But there is evidence that a single hydrogen can be shared between two atoms with 2 electrons. Duh. Okay, see? Don't even worry about that. But we're going to pretend that that world doesn't exist. If it's got to be 1, and these two carbons are identical, so on one of them, I need to have the new hydrogen. And then the other should have what? Some of you are saying lone pair. Where would that have come from? So it should have an empty p orbital on this carbon, right? Because you've taken the 2 pi electrons and you've moved them into this bond. I mean, we can highlight that by using a blue line for the pi electrons, and now they're here. So that other carbon now should have an empty p orbital on it and a positive charge. Okay? So that's chapter 10 and 11 stuff. If you want to go further down the rabbit hole, we have another addition reaction we could do here because we have a negatively charged chloro, which could now be our nucleophile, with the HOMO being lone pairs on chlorine. And this positively charged carbon can be our electrophile, and the LUMO would be what? Empty p orbital on the positively charged carbon. Good. The reason it's that as opposed to any of the antibonding orbitals is that non-bonding empty orbitals are always lower in energy than our antibonding orbitals. So HOMO attacks LUMO, and you've just predicted a chapter 10/11 reaction without knowing anything other than HOMO attacks LUMO. Okay? And there's more. I mean, but any questions you want to ask about that example? Yeah?
So right there where they're attacking, does it essentially become rehybridize into an sp3?
Yes. As the attacking happens, the carbon that gets a new bond has to rehybridize into sp3. Yep. And later on, as we get to these reactions, I'll show you some animations that make that point more clear. Okay, others? Yeah.
So, oh, sorry.
Okay, here and then.
With 3 hydrogens on one side and 2 on the other, would that be an unstable molecule because one carbon doesn't meet the octet rule?
Would that be an unstable molecule because one carbon doesn't meet the octet rule? Yes, there is. And another way of saying that is there is a low energy empty orbital here ready to do something. This type of intermediate is called a carbocation, and it is pretty unstable, high in energy. So actually, you wouldn't isolate this. In reality, you would only get this. Yep. Okay, and then.
Some product you had down there. Why did you just draw 1 hydrogen? Was that just?
Sorry, I mean, I could have drawn all the hydrogens. You never have to draw all the hydrogens unless you're going to actually write out the C. So no fair doing this and only drawing 1 hydrogen. If you draw out the letter C, you have to put all the hydrogens on. I don't know. I didn't make up the rules, but that's the way they are. Okay, and yes?
With the molecule that has 3 hydrogens on one side and 2 on the other,
Yeah.
I'm confused. Didn't we lose an electron? Or should there be 13 electrons, but there's only 6 bonds?
So 2, 4, 6, 8, 10, 12 electrons in this intermediate. 2, 4, 6, 8, 10, 12 electrons in the starting material. Yep. So we haven't lost any electrons.
But like, I guess what I'm saying is, aren't you adding one with adding the hydrogens? So shouldn't there be 13?
No, actually, good question. When we attack the LUMO, the hydrogen goes with, but doesn't take its electrons. The electrons that were in the hydrogen-chlorine bond end up on chlorine. Yep. Good. All right. One more addition reaction because I can't resist. I sort of just geek out on helping you see what happens in the rest of OChem. This carbonyl compound, if I told you it was an electrophile, what would you say the LUMO was? Carbon, oxygen, pi star, which we're going to draw kind of like 2 p orbitals. We're looking at it on the side. The hydrogen, carbon, hydrogen, and oxygen are all in the same plane. We're sort of looking at this molecule on the side. I haven't drawn the plane. And we have a node in between the 2 carbons. So, and then I'm going to give you a simple nucleophile, which is OH minus. You've seen that before. The HOMO is non-bonding lone pairs on oxygen. HOMO attacks LUMO, so we would draw electrons from here, but we've got 2 different spots of the LUMO, one on carbon, one on oxygen. Which one should we attack? Use what I told you about HCl to figure that out here. You're saying carbon, right? And that is because carbon is less electronegative than oxygen. So our nucleophile should attack the more electron poor part of our molecule. So HOMO attacks LUMO, and it's actually got to come in from above the plane of the oxygen, hydrogen, and hydrogen atoms, okay? Because that's where the pi star is. Now we've dumped electrons into a pi star antibonding orbital, so what do we have to do? Got to break that bond. Electrons, because we're making a new bond with, the arrow tells you that you're making a new bond with this carbon and breaking the pi bond with oxygen, and so you would predict an intermediate that would look something like this. 1 negatively charged oxygen here and an OH there. This isn't the final product, that's just an intermediate. We're just dealing with the first step of the reaction. But that's something that you won't really see again until 352. Okay? There are elimination reactions. So if, and some of these are, you'll see some this semester. One that is sort of simple enough is is an elimination reaction that just happens on a single molecule. I feel like I need to shrink all of this so that we have room. There. So some molecules are poised to react on their own. This is actually an intermediate in a reaction you'll learn in 352. If I had to choose the HOMO of this molecule, again, I would say probably lone pairs on oxygen. There are lone pairs on each of the other heteroatoms there, oxygen, chlorine, and the other oxygen. Chlorine's more electronegative, which means its lone pairs are, or rather, chlorine is the negatively charged oxygen. The negative charge tells you this is the highest energy lone pair, sorry. Now, if I had to choose a LUMO, I will tell you that I would choose the carbon chloro sigma star. You can figure that out in a couple of ways. We'll learn some of that in chapter 2. But for now, I will just tell you, you can go look up that carbon chlorine bonds are weaker than carbon oxygen bonds. It has to do with the fact that chloro is bigger than carbon, whereas oxygen is about the same size, and shorter bonds are stronger. If an atom is bigger, the bond has to be longer because it can't get any closer. So carbon chlorine bonds are weaker than carbon oxygen bonds. And so we could draw the carbon chlorine sigma star, a lobe here and another lobe there. Here a lobe, there a lobe, everywhere a lobe. Sorry, now we can do in the same molecule, HOMO attacks LUMO. It can react with itself. Lone pair electrons can line up with and dump into that sigma star. We're going to make a new bond with this carbon, and then this bond breaks. That's an example of an elimination reaction. Here's the new pi bond that we made. And then Cl minus took its electrons and left because we broke the carbon chlorine bond. Okay? In particular, you're just looking for the general gist that HOMO attacks LUMO. This specific mechanistic step isn't important at this stage. You'll learn it later. I just want you to see how these things apply. Lastly, let's talk about substitution reactions because you will see this in 351. Let's use CH3I. Iodide is not particularly electronegative, but it is large. And carbon iodide bonds are long and relatively weak. And if a bond is weak, that means that its sigma star is low in energy. So I'm going to use that as the LUMO. If you would not have yet been able to predict that the carbon iodide sigma star is the LUMO, that's okay. We're going to develop some tools in chapter 2 and in other chapters to help you with that. We'll draw the sigma star as we've done. And then suppose we have, I don't know. Oh, no, this would be good. Let's have some R group that we don't care what it is, and then we'll use sulfur as a nucleophile. This type of molecule you'll learn later is called a thiolate. And of course, for HOMO, you would choose non-bonding lone pairs. You get it? You see that that's starting to be a little bit easier than trying to draw out the whole dang energy diagram. You know you can ignore sigma bonds if there's lone pairs present as the HOMO, right? So HOMO attacks LUMO, sulfur attacks at carbon. Again, to rationalize why it's this way, you have to know something about one of the products of the reaction. I make a new carbon sulfur bond, and I minus is, I leaves with the electrons. Now, I minus is pretty stable on its own. We're going to learn why. In contrast, if S had attacked I, the electrons would have gone on to C, and C with a negative charge on it isn't particularly stable. So this just happens to be the most favorable way for the reaction to go. Okay? So all of that's sort of a summary of 351 and 352. And, you know, come back to this occasionally to remind yourself what's going on. This is most useful when you're trying to work out the mechanism of a reaction that is unfamiliar. Perhaps the reaction is actually one you've dealt with before, but the players are a little bit different. You haven't seen those specific molecules before. Go back to HOMO attacks LUMO, and you probably have the first step. And for multi-step reactions, you can do that all the way through. Okay, so end chapter 1, introduction, and that was sort of the last part of chapter 2. Now we're going to deal with acid-base chemistry. And I am just pausing to confirm that we are recording and we are getting audio. I've been recording lectures since the beginning of the pandemic. One would think that by now I would know how to capture audio, but it's always silly. Yes?
Real quick before we move on, just explain one more time how we know that the carbon iodide is in the LUMO as opposed to...
Yes, as opposed to the carbon hydrogen. Why is the carbon iodide sigma star the LUMO? You have to know some things about carbon, bonds between carbon and other things. You can look up in the back of your textbook bond strengths, and you'll see that carbon iodide sigma bonds are much weaker than, say, a carbon hydrogen bond. Bond weakness refers to how low, or strength refers to how low in energy a carbon hydrogen sigma bonding orbital is versus a carbon iodide bonding orbital. And as we've said, if a sigma bonding orbital is not very low in energy, then the sigma star anti-bonding orbital is correspondingly not that much higher in energy than our starting atomic orbitals were. So that's the reasoning. We're gonna talk again about bonds with iodide and how to think about them, but so it's okay if looking at that, you were thinking about some kind of sigma star, but you weren't totally sure which one it was. You'll get used to recognizing the carbon halide bond as being the one to worry about. Yeah?
Is the carbon iodide bond weaker because the distance between the nuclei is greater?
Yes. Is the carbon iodide bond weaker because the distance between the nuclei is greater? Yes. Further away from the nucleus is higher in energy. Longer bonds are weaker bonds. Go ahead.
Why is this a substitution reaction, but the one with the chlorine right next to it is an addition reaction? Because it's keeping the chlorine off and replacing it, right?
Up here?
On the left.
On the left. Oh, right. Well, it depends on... Sorry, what's the Obi-Wan Kenobi line? What I told you was true from a certain point of view, right? It looks like a substitution reaction for the hydrogen, right? But from the perspective of the carbon, it's an addition reaction. We are going to be pretty carbocentric in how we describe reactions, so that's why. Good. All right. Sorry. If you should visit my office, and I encourage you to do so, to admire all of my Star Wars Legos, you will see that I am kind of a Star Wars nerd. For example, this week, the Mandalorian trailer for Season 3 of The Mandalorian dropped, and there's a possibility that we saw Sabine Wren in one of those. That doesn't mean anything to some of you, but, you know, fellow nerds, you got me? Okay, yeah. Okay. Acid-base chemistry. This is going to review a lot of things you know in Gen Chem, but it's going to put an organic spin on it. Your goal is to learn what makes a good nucleophile good, and we'll later learn about what makes a good electrophile good. In order to do this, we need to introduce the concept of pKa, and so just a brief review of that. pKa is a measure of the acidity of some acid relative to hydronium. So you add HA to H2O. There's some equilibrium constant that gives you H3O plus and A minus. Okay, that should look painfully familiar. It's useful to define some terms. On this side of the equation, we have our acid, and this one acts as a base because it gets the hydrogen or the proton. On this side, we've got the conjugate acid of our base, water, and this is the conjugate base of the acid. So you can think of acid-base reactions as involving trading who's got the proton and trading who's the acid or the base. These reactions are, depending on what the equilibrium constant are reversible, and so you can think about them from either direction, but this is sort of how we're going to set it up. Now you can measure that equilibrium constant. We would define that as KEQ equals H3O plus A minus over H2O times HA. Now in Gen Chem they told you that these are really not concentrations, they're activities, and they maybe told you something about an activity coefficient, which you promptly ignored because most of the time we do, but they probably told you that the activity of a pure substance is 1, and therefore we're just going to ignore water. That's okay, but you can also deal with this by just accepting the concentration of water. It is, in a solution, about 55 molar. If you take the density of water and its molecular weight and so on, you can calculate the concentration of water as it sits. That concentration is so huge that it is essentially constant. It doesn't change as a function of the reaction. And so what we will do, because we like to group constants together, is we'll go ahead and multiply both sides of the equation by the concentration of water. Oops. Slide that guy over there. Okay. So we're going to fold the concentration of water into our equilibrium constant. And now we've got something that looks a little bit more familiar. This is the so-called acid dissociation constant, Ka. Some of you learned perhaps that acids dissociate and go from HA to H plus and A minus. That is true only in the gas phase. In water, when people say this, it's shorthand for this. So there's no such thing as H plus in water, it's just H3O plus. Okay, so I'm going to always write H3O plus or HA, never going to show H plus on its own, because most of the stuff we're talking about happens in solution rather than in space. Now, equilibrium constants can vary over several orders of magnitude, and sometimes we get lazy and don't want to either write all those zeros or even use scientific notation. So instead, we'll use the logarithm to make this more manageable. We'll use the negative log. The reason we do this is so that the numbers for Ka track with free energy. Lower Ka numbers mean more acidic. Minus log of Ka, and that is going to be actually defined as pKa. I just learned this week that P stands for power. I never knew that. So power of 10 logarithm or something, I don't know. pKa equals the natural or the logarithm of, then this expression, H3O plus A minus HA. And we can further, let's see, I want to make sure I do this right. That's, I think, negative log, yeah, thank you, sorry. So we can rewrite this equation in a slightly more useful form. Properties of logarithms allow you to take products and turn them into logarithm of a product is the same as the sum of the logs of the individual whatever. Minus log of H3O plus is really just pH. And then you've got minus log of A minus over HA. That's, and maybe you've also seen it in this form, I don't know. pH equals log of HA over A. You've used that before to calculate if I know the pKa of an acid that I'm using, and I know I can calculate what ratio of acid to conjugate base I must use to get a determined pH. That's buffer preparation, which is a great skill. We're going to use this in an entirely different way. We're going to use this to determine, under given conditions in aqueous solution, whether the acid form or the conjugate base form dominates. To do this, we simply have to subtract pH from both sides. And that will give us pKa minus pH equals log of HA over A. So when we have an acid in solution, and when I ask you these questions, we'll be assuming that the pH of the solution is constant, because the organic acids that we deal with are going to be present in fairly low concentration. pKa minus pH, so based on what the pH is and what the pKa of my acid is, I now know whether the acid or base form dominates. For example, let's choose HCl as our acid of choice. Let's choose it as our choice. That was horribly redundant, sorry. The pKa of HCl is like, and I might get this wrong, but it's fine, -7. Okay, and let's suppose we're in water at pH of 2. So, pH is greater than pKa. This number is negative, so which form dominates? Acid form, HCl, or Cl minus? Okay, if it's negative on this side, the log of, no, how do you get a how do you get a logarithm that turns out to be negative? The number has to be less than 1, right? Which means the denominator is bigger. Okay, yeah?
I was just going to say, the pKa of water is 2, but the pH of water is 7.
Right. The pH of pure water is 7, you're right. What I'm saying is we have prepared a buffer and the pH is held constant. That's backwards maybe from Gen Chem, where you're like, what is the pH if I do this? We're going to say pH is constant. The reason we do that, by the way, is because in biology, that's true. That's really tightly regulated. Your blood pH is 7.4. If it gets apart from that, weird things start to happen. You've heard of respiratory alkalosis, where you're hyperventilating and your blood pH changes because you're expelling too much CO2, your blood's getting more alkaline. Anyway, so we're going to assume that for a lot of what you're learning here is to prepare you for biochemistry. So we're going to assume that pH is constant. Right. Okay, so we'll come back to that. If the pH of the solution is greater than the pKa, the acid is actually in its conjugate base form. If the pH is less than pKa, the acid is in its acidic form. What this tells you, by the way, is when you use HCl in acid, when you buy concentrated HCl, what you are buying is H3O plus and Cl minus. All right, so let's talk about now, let's talk about these pKa numbers and get a general feel for what they should be. Though we can pause for any other questions you have. Yes?
So just making sure in this case HCl is in its acidic form?
at pH 2, HCl should be in its negative conjugate base form because the pH is greater than the pKa of the acid. Yes?
Can you repeat that again? You said when pH is less than pKa, the conjugate is in its acid form?
So I do this every semester, and some of you reason better in equations, others reason better in words. I stumble over my words and sometimes say the wrong thing often. It's really annoying. It's really annoying to have a conversation with me, actually. When we're at home playing card games or something like that, I can't actually think to play the cards and talk at the same time. So there's really dramatic lulls in the conversation as you can, it's like I have the spinning rainbow thing buffering going on. My son's just the same way, and he came to my office the other day and we played a game of chess over lunch. And you can imagine how interesting and fast that conversation was as we were both trying to think and talk at the same time. In any case, I have to look at this equation to say the right words, okay? So, if this number is negative, this number must be greater than that number. In other words, if pH is greater than pKa, then concentration of conjugate base must be greater than concentration of the acid. Can we take a minute and verify that that's true? We can also say that if pH is less than pKa, then this number will be positive, and therefore the concentration HA will be, well, delete. Maybe we'll just do it this way. The concentration of HA will be greater than the concentration of A minus. I realize those are still equations and not words. Yes?
So is the pKa here -7 or is it supposed to be like -7?
I'm sorry, I was in a hurry. pKa equals -7 pH of water at this buffered concentration is 2. Yes?
So, I'm trying to figure this different way. So, right now, if we put those over together, we get -5.
Yep.
So, -5 means that the acid form is
Actually, let's see, -7 minus 2 is -9.
oh, that makes more sense. So, we have -9.
Yes.
So that means the acid is preferred.
Nope, conjugate base is preferred. And this is a property of logarithms. Let me just show you this. I guess I oversimplified when I told you if you could count and divide by 2, it would be enough. You don't have to do logarithms in your head, but it's helpful to know the logarithm of 1 is 0. The logarithm of 10 is 1. The logarithm of 0.1 is -1. So if a ratio is less than 1, the log should be negative. Incidentally, this tells you that if pH equals pKa, what should the ratio be? 1, right? So when pH equals pKa, the concentration of acid versus its conjugate base is the same. What that would mean is that you can interpret pKa as the pH at which the acid would exist in a 50-50 equilibrium with its conjugate base. Okay. Yes?
I had a question just up at the beginning where you wrote the general equation for the acid base and conjugation conjugate base. You just put one lone pair on the oxygen.
Yes. I just put one lone pair on the oxygen. Sometimes we won't even draw the lone pairs. You just have to know from the structure that they're there, and I'm only drawing one because we only need one. Yep. Okay. So we'll come back to that with some example problems, but that sets the stage for what we want to do now, which is just look at some trends in pKa's. There's only a couple of pKa numbers I want you to know by heart. Others you'll have on a table, but you should be able to reason your way through. Because of what we have done here, you can see that the more negative pKa is, the smaller pKa is, the stronger the acid will be. Okay? Stronger acids have conjugate bases that dominate. So let's just talk about that for a minute. I'm going to write HA here. I'm going to write A minus here. That's acid in conjugate base form. And in the middle, we're going to put pKa. And we're just going to work through a little bit of a table. I'll start with the strongest acids. HI has a pKa of like minus 11. So that's one of the strongest acids we know. See that this negative number, if you were comparing it to like water, pH of 7, the acid would lose its proton to hydronium and everything would exist as just the conjugate base, which in this case is I minus, iodide. And the other hydrohalide acids are also quite acidic, though not as acidic as HI. And in fact, as we move up the periodic table, we're going to find, as we move up a column of the periodic table, we're going to find that acidity decreases. By the time you get to fluorine, the pKa is 4. We'll talk about how to rationalize that. Let me draw the conjugate bases, Br minus and Cl minus. Smaller pK, more negative pKa numbers mean more acidic or stronger acid. That's also the same way as saying lower energy sigma star. And then over here, we're going to see that that strong acids are strong because their conjugate bases are weak. Weaker conjugate base. That's another way of saying a more stable conjugate base, which is another way of saying a relatively low energy, highest occupied molecular orbital, which is usually going to be lone pairs. Yes?
Is there a unified chart of pKa somewhere online, or is there one that we have
So there in your textbook, there's a chart of pKa's in chapter 2. There's also in the appendix of your textbook, I believe, another table that's a little bit more complete. Honestly, if you find an acid you don't know, you can Google its pKa, and if it's known, you can find it probably in the Wikipedia article somewhere. A lot of these are tabulated and known. You won't have to memorize these, for example. But I will be asking you to rationalize why some molecules, based on structure, why one molecule is more acidic than the other. We're not quite there yet. Let's review some of the other acids. You've got hydronium, which I will draw like this, and its conjugate base is water. Hydronium is a positively charged acid that has a neutral conjugate base. These were neutral acids that have negatively charged conjugate bases, so we're going to see both situations. The pKa of hydronium is close to -2. And that's a useful number to know because it also applies if we replace one of the hydrogens on hydronium with some carbon. So this is hydronium. We're going to call this an oxonium ion. It's a protonated alcohol. The conjugate base of the oxonium ion is some alcohol. I've left the R group general, though I suppose we can be more specific and say it's something alkyl. I'm just going to represent that with a methyl group, though we will be able to replace the methyl group with other hydrocarbon-like things in general and get the same number. Okay? So -2 is the pKa of hydronium and protonated alcohols. That's one of the ones to memorize. If you can memorize -2, that's good. We can continue on. Let's see, the conjugate base of HF is fluoride ion. And notice that as we're going down, as we increase in pKa numbers, going this way in the table, we're going to less acidic or weaker acids or higher energy sigma stars that are starting to be less accessible. Yeah?
Maybe just as a clarification for me, but I know that we have to have pH and pKa to see the ratio. Are we always assuming that the pH is constant at 2, like you're saying?
Are we always assuming the pH is constant at 2? No. In a problem, you'll see in the practice exam, I'll give you a problem where I show you this horrible molecule and I say, what should be its formal charge at pH, whatever. It might be 7, it might be 8, it might be 2, and then you'll have to decide all of the acidic groups in the molecule based on their individual pKa's compared to the pH, what should their form be, acid or conjugate base? Yeah. Yes?
So why does it go from like iodine, bromine, chlorine, -11, -9, -7, and then 4, like randomly just like jumps up?
Okay.
4.
Yeah, so we just as well talk about that at this point. You're noticing that among the halides, HI -11, HBr, that's a factor of 100 less acidic, HCl, another factor of 100 less acidic, and then boom, HF, almost 100 billion times less acidic, right? That's a pretty big difference. So we can talk about the differences between HF and HI and HBr. The best way to illustrate this, though, is probably to use the Spartan app, and I'm going to actually draw HF. Okay? And I want you to just imagine and compare that bond size, that bond length, and atom size for HF. Whoa. With if we replace the F with Cl. Notice the bond is a little longer and Cl is a little bigger. We go to Br minus. The bond is even longer because Br minus is bigger. And then we go iodide and the bond is quite long. So we're going to see it tracks with bond strength, but it doesn't track with electronegativity. And we'll talk about that next time. All right, happy Friday. Have a good weekend. Be safe. See you Monday.